Hi, we're from the University of Oxford, and I will be presenting our paper, Get to the Point, Learning Lidar Place Recognition and Metric Localization Using Overhead Imagery.
Standard Lidar localization requires a prior Lidar map. In the absence of prior sensor maps, data that are freely available from the internet can be utilized. Public overhead imagery is a resource readily available almost everywhere. It can act as a map proxy for range sensor localization, as overhead imagery and range sensors often capture the same entities despite being different forms of data. The modality transfer is non-trivial. Here, the two patches in the overhead image corresponds to different LiDAR data due to LiDAR's limited field of view, making standard image-to-image transfer methods like cycloGAN unsuitable. Instead, we show how overhead imagery can be transformed into a collection of 2D points, allowing for direct comparison against ground LiDAR data for registration and place recognition. To address the modality difference, our method first learns an occupancy image from an overhead image, where the pixel value indicates the likelihood of each pixel lying on occupied space or free space when scanned by a LiDAR sensor. We then take the first occupied pixel along each azimuth as a point to form a point cloud, and do the same for a LiDAR image with some pose offset. Our method learns the point cloud registration to compute the relative rotation and translation offsets between the overhead image and the LiDAR image. After predicting an occupancy image and subsequently converting into points, our method learns a global descriptor for each point set. For place recognition, the match is found by taking the distance in descriptor space between a LiDAR image and all overhead images. Our networks are trained in 3 stages. First, we learn to predict occupancy images from overhead imagery. Next, we learn the point cloud registration. Finally, we learn a global descriptor for place recognition. To learn the occupancy images, we first produce a certainty mask. Based on prior knowledge, given a LiDAR image, ray tracing along each azimuth, if a pixel has range return, it is likely on occupied space. We are certain that pixels in front of the first range return along each azimuth are on free space. For pixels with no return and behind the first return, we are uncertain. We can produce a certainty mask where 1 indicates we are certain about the occupancy of the pixel and 0 indicates otherwise. We also make use of publicly available Google roadmap imagery as an additional input. We use an UNet to learn the occupancy images where the loss function is weighted binary cross-entropy loss, where the weight is the mask and the label is the binary LiDAR image. The next step is learning point registration, which we make use of deep closest point. First, given the learned occupancy image and a LiDAR image with sufficient overlap, we ray trace along each azimuth and represent them as n two-dimensional points. The 2 point sets are passed through a joint DGCNN plus transformer module, which outputs a d-dimensional local descriptor for each point. This results in an n by d array of local descriptors for each point set. The local descriptors are then matched based on their Euclidean distances to form soft correspondences. Finally, singular value composition is performed on the correspondences to produce the relative rotation and translation. We apply an L1 loss on the pose for training modules associated with DCP. To learn place recognition, we take triplet pairs of an anchor LiDAR image, a positive overhead sample, and a negative overhead sample. The positive overhead sample is queried at a proximal location to where the anchor LiDAR image is taken, and the negative overhead sample is far from the LiDAR image. We represent all images as points using the aforementioned method. Next, taking the DGCNN module trained previously when learning point cloud registration, we can produce an n by d array of local descriptors per point cloud. Each of these gets passed through a nav-lat layer, which produces a k-dimensional global descriptor per each local descriptor array. Finally, we apply a standard triplet loss to optimize the nav-lat layer. Note that we were using the DGCNN module from DCP to produce the local descriptors, and the nav-lat layer only needs to convert an optimized local descriptor array into a global descriptor vector. This minimizes the additional training needed. Here we show results for place recognition on the Oxford dataset. Over half of all top-line retrievals fall within 50 meters of the true position. Here we show results for metric localization. We use an initial offset with large heading difference from -pi to pi. The solution converges with reasonable heading error for most cases. Thanks for watching this video.